Hey guys, in this definition we're going to look at how to create a voxelized representation of an object. Now this is a script I put together a while back, but I'm going to show it with some modifications for this tutorial, so just follow along. I'm going to get rid of this, and it's going to take a while because there are a lot of meshes there, and once it finishes we'll crack open a new definition. Alright, cool. So we're going to get started with a sphere. In fact, I'm just going to use a mesh sphere for now. I'm going to throw down a slider for my radius. Give that a maximum value of 100, and plug that in. Cool. And so now this is going to feed into a bounding box. This bounding box is going to be the sort of crux of this definition, in a sense. So what we're going to do is we're going to obtain some information about this box using box properties. This is quite useful. It tells us a lot about the box. The center of the box, the diagonal vector, which can also be interpreted as the size of the box in each direction, the area of the box, the volume of the box, and the degeneracy of the box. So we're going to use this diagonal vector. What we're going to do is we are going to multiply it. We're going to multiply this vector by a slider. I'm going to give it a maximum value of 10, and there we go. And then what I'm going to do is I'm going to deconstruct the vector on this side. That's another thing, you can multiply vectors just by a single value, and that will that'll multiply all three values in every direction, kind of like a uniform scale of sorts. Alright, and so then on this side we're going to use an expression to find the ceiling of x. And so we're going to do this for all three of our outputs. Just going to align them nicely, and then what we're also going to do is we are going to divide the size of the box, which is this here, by this ceiling value. So we're going to do this for all three dimensions, and there we go. And so now we have enough information to continue. So what we're going to do is we're going to evaluate the box. And what we're also going to need is a range component. Actually, we're going to need several range components. One for all three of these. And so we're going to use these to evaluate this box. So we also need to plug the box in here, and we're going to get a series of planes. And so I'm glad I did this now, because I can immediately see that this multiplier is set way too high. That is far too many divisions to be creating. And so at this point I'm also going to check that my my voxel resolution is correct. And so the way I'm going to do that is with a center box, and on this side I'm going to convert that into a mesh box. And we just need to set an X, Y, and Z size, which, if I'm not mistaken, should be these values over here. And so then, cool, that looks to be, oh, almost. What we do need to do, what we'll also do, is we will move these mesh boxes to each of these points. And so it looks like we are out just by a factor of 2, So what I'm going to do is I'm going to create an expression for this, and I'm going to go x over 2 times y. So x and y. Whoops. Put those in brackets. Alright, there we go. And so we can see that's lining up, or those edges are all now lining up properly. So I'm going to do the same thing for all 3 of these. Make 3 copies and plug our values in. And plug those into our y and z. And so now we have a whole lot of boxes that have their corners touching perfectly, as we'd expect. And what I'm also going to do is I am going to put down an integer on this side for the number of divisions for my boxes. I'll set that to integers because we don't want, well, at least at the moment I don't want these higher resolution boxes. We've still got this one getting in the way, but that's alright. It's not actually a problem anymore. Alright, cool. So, of course, this is still not correct because we, well, we've got a diagonal line, not the correct number of, not a correct sort of volume of boxes. So what we need to do is we need to cross-reference. We need to cross-reference all 3 of these ranges, and then we'll plug them into here. And preview that off, and there we go. There are all our boxes. Alright, so the simplest way at this point would be to simply do a collision test. And so I'm just going to lock the solver really quickly. And so my object for collision is the sphere, and my obstacles for collision are all of these boxes here. So now I'm just going to preview these off, and I'm going to unlock the solver. And so now we can run this through a cull pattern. Oh. Actually, it looks like I needed to do that the other way around. So I'll just unplug this. Alright, and there we go. Let me preview my box off. Huh, that's interesting. Looks like we're getting a couple of extra results for some reason. Let me just see what happens if we were to tune this a little bit. So maybe I'll set this to 0.25. Nope. Apparently our sphere extends a little bit beyond this shape. Maybe I'll just try with a different object. So let me see. Let's just try a normal sphere. Alright, so now here we go. Here we can begin to see the issue with this sort of method. Basically, we could use this collision between one and many objects, but it is a very resource intensive process, and also for some reason, I'm really not sure why these are popping up, but they are. Yeah, it's not doing it correctly, but it is giving us the voxelized representation of the sphere. So we could use this method if we want. there's nothing wrong with that, apart from the fact that it would be incredibly resource intensive, which is why I developed a slightly different method. So we're going to delete these, and I'll just go back to my normal sphere, or my mesh sphere, and we'll continue along. So instead of doing this, what we're going to do is we are going to take the distance between each of these evaluate box points, and and I also need to do a brep closest point. Or actually, this component that we're going to plug into next entirely depends on what object you are using, or what type of object you are using. And so it looks like I'm actually using a mesh closest point, a mesh, so I want to use a mesh closest point. So I'm going to plug the point to test from here, and the mesh in over here. And so this is going to give me the closest point on all of these meshes. If you are using brep closest point, you'll notice that it already provides you with a distance value, but the mesh closest point does not. So plug these in, and this is going to give us a distance. Alright, and so now what we need to do is basically this new method that I came up with looks at it from a more mathematical standpoint. And so if we have a box, let me just bake this box into here and move it out here. Basically what it's going to do is it's going to look at the point, and so if the point is here, it's going to measure the distance from the center of this box to this point here, and if it is less than the distance from here to the corner of this box, then it will not include it in the final result. And so the way we do that is with a mathematical expression. So we need this will be our x, y, and z values. So we have x, y, and z. And so what we're going to do is we're going to take the hypotenuse of x and y, and we're also going to then take the hypotenuse of x and y and z, because we're working with three-dimensional trig here. And so we get a value of 3.33. And so what we're going to then say is, actually I can just work this in here. No, I won't even do that. I'll just use an operator. So if this distance is smaller than this distance, then true. And so what we're going to do is we're going to create a cull pattern for all of these points, and we're going to use this pattern here. And then all we need to do is replace this transformation vector. And we can see we get our voxelized sphere. And so what's really good about this method is that it you don't need to create all the geometry boxes first and then test for collision. You do it from a more analytical method using points, which means you do not actually need to create all the geometry here, which does save a bit of resources here. And testing for a collision between two objects is always going to be more mathematical, more resource intensive than a pretty straightforward mathematical equation. Finding the hypotenuse, it's pretty simple. So we could plug any shape we want into here, albeit a sphere, maybe I'll just show that this has a bit more versatility to it. And I'll plug my geometry in, and I'm going to change my my scaling factor. And you know what, I'll keep the Z at 1. We can preview off this sphere, and I'll just drag everything. If you haven't come across this, Control and Shift takes all the inputs out, and we can plug it into something else, and then we just need to reconnect our scale non-uniform. And so now if we were to go back and look at our voxels, they all line up again. Key thing to note actually that I don't think I pointed out before, I've set up this definition by taking the ceiling. That ensures that, that means that the voxels are going to go sort of outside the definition of the box, but this means that you won't get any voxels sort of right up tight against your collision geometry that you're testing with, which I find to work just a bit better for purposes of creating this sort of voxel. Alright, so now we can increase our multiplier, and we can see we do get a pretty quick response on our geometry. We could probably bump this up again. Maybe we'll try 2. Now it's going to take a bit of time, but of course it would take nowhere near as long as the collision test did. Cool, so we'll just wait this out, and there we go. Maybe I'll turn the bounding box off, see if that helps us see what's going on here, and then we'll turn, oh no, mesh edges are off as well. Okay, so we can see that's getting pretty slow. I'll take this back to 0.5. Alright, and so now what we can do at this stage, this is just a little extra that I included in the definition I did a while back. I'm going to start by throwing down a data dam. This is quite a useful component. It basically allows you to send through data at your discretion. So if you do have a pretty heavy definition, no changes will happen after this point unless you press the play button, and then everything gets fed through. Cool. So now what we can do is we can deconstruct, not deconstruct, we want to explode the meshes, and we're going to want to flatten this list, and then we are going to use face normals, and this is going to give us the center of each face. And then we're just going to flatten this list as well, and from here what I'm going to do is I'm going to use a cull duplicates. So this will basically look at the list of points, and anywhere that there are points of the same value, well, we sort of have a few options. We can leave one, we can cull all, or we can average. And what I want to do is I want to cull all duplicates. And so then Okay, so that takes our count down from 23,000 to about 6,000. And so then what we can do is we can use sets actually. Sorry. I'm going to use what's called a member index. So what we can do is we can search for all of these items and their occurrence in this list. And that's going to take a while to load. Basically, this is going to tell me I'm trying to get rid of all duplicate faces in this mesh, and then I'm trying to find the index of each of those faces, and that'll allow me to create a sort of a shell representation of this piece of geometry in a few moments. Alright, so now we can use a list item component on these faces here. I'll just preview this off, lock my solver, and so the member index has searched for all of these items in this list. It's given us a whole lot of index numbers, which I'm going to plug into my list item, and so then it's going to spit out, what, 6,000 items again, and then we can use our, okay, wait, we'll just, we'll let that do its thing. Oh, okay, it was really quick. And so there we go, there are all our external mesh faces. And now we're just going to use a Weaverbird join. And, oops. What else do I have turned on? A few things. Alright, and then we're going to use a weld vertices component. And what you'll notice at this point is it looks like we've got two different meshes, because obviously there's going to be an interior and an exterior. So what I might want to do is remove the interior. So what I can do is I've got this component called disjoint mesh, which will, after we've welded the vertices, it'll look for any meshes that are basically separate from each other. They don't have any sort of adjoining geometry or vertices. And so we get two meshes here, and I can just dispatch those to get my inside and my outside. And then, you know, if I wanted, I could run this through a Catmull Clark. Or I could use a Weaverbird Laplacian, which will sort of smooth out my mesh. If I just give it a bunch of, if I just bump up my iterations here, we can slowly, okay, it looks like that is my interior one. Nope, that's the exterior one. And so you can see we're getting this representation of our mesh, of our object. Well, obviously this was not the point that we were trying to achieve when we were voxelizing it, but it is just a cool sort of thing that you can do with it, which you may think is a bit unnecessary. But there we go. That's how we can create a voxelized object. I'll just bake this out so we can have a look at it. There we go. There is our mesh. Hope you enjoyed it.